Molecules.
Goodness. So today I'm going to start the day by throwing a lot of information at you. I know you're going, what's that normal? But then I hope to help you with that information after it's all out there. The fact of the matter is one of the sheets that you picked up, you may have already printed off, but it is a step-by-step guide as to how to do Lewis dot structure, which we talked about in the last 2 Wednesdays. You have to be able to get the Lewis dot structure and understand the difference between bonding pairs and non-bonding pairs in order to determine the shape of the molecule. The shape of the molecule is determined using VSEPR theory, which stands for valence shell electron pair repulsion theory. Essentially, with valence shell electron pair repulsion, let's just break that apart. Valence shell electrons. Hey, those are the electrons that we've been adding up to develop our Lewis structures. Pair repulsion, meaning those pairs of electrons are going to repulse one another because they are negatively charged species. And they are going to repulse one another so that they're as far away from each other as possible. That creates the shapes that we observe for our molecules. Now, I have one that I call the electronic or electron geometry, which there are only 5 electron geometries. And then there is the molecular geometry. The difference between the electron geometry and the molecular geometry, as we will hear, is whether or not there is lone pairs present. The second thing we're going to be talking about today is valence bond theory. Valence bond theory helps to explain these shapes that are observed. And then finally, we'll talk about whether a molecule is polar or non-polar. And that's going to bring in our electronegativity. But this all is based off of those Lewis structures to begin with. And then we apply these different theories, these different concepts to those Lewis structures to determine shapes, to determine the hybridization on the central atom, to determine the bond angles, to determine the molecular polarity. Now, you may wonder, how the heck, I mean, we can't see an individual molecule. How do we know the shape? We have instruments that are called X-ray diffraction instruments. And with X-ray diffraction, we can actually see the shapes of the molecules. So it's through the experimentation that these shapes have arisen. Now, on Blackboard, in your flipped classroom, not only do you have my videos, oh dear, but there are a couple of other videos, not that you can read them on this screen. One is VSEPR theory. I love this video because, and I'm about to show it to you in class. I like this video because it does a much better job of illustrating things in 3D. So I put that video, the link to that video up there so that you can re-watch this video as frequently as you need in order to get a grasp on VSEPR theory. The second one is valence bond theory, which again, you can't read. And I'm going to show that video. And again, valence bond theory allows us to determine the hybridization on the central atom. Now I'm going to take the information, and I'm going to simplify that information because valence bond theory it's useful, but I know it can be a lot to digest. So I do have a way to simplify that one. And then the other thing that you're going to find at the very bottom is if you need more examples of Lewis structures, how I took the Lewis structure and got the electron geometry and the molecular geometry and the hybridization and the molecule polarity. I have made around 100 videos, one molecule at a time. So you can watch what you need, but you don't have to keep watching if you don't want to get it. So there is that list of videos and they have the links to them. So that is more that you can see once this class is over, and it's whatever you need in order to start to really grasp it. Because I'll do some problems, but I'm limited on time on how many I can do. I can't do 100 of them. So. Okay, VSEPR theory.
Chemists use valence shelled electron pair repulsion, or VSEPR theory, to account for the shapes of molecules. The theory is based on the idea that like charges repel each other until repulsions are minimized. The like charges in this case are the groups of valence electrons around a central atom in a molecule or ion. We'll represent them as bars attached to a sphere and show the electrostatic repulsions as yellow arrows of varying width. The simplest case has two negative groups around a central atom. At any angle less than 180 degrees, electrostatic repulsions push the bars apart. Repulsions are minimized when the bars attain a linear arrangement. Electron groups can be single bonds, as in gaseous beryllium fluoride, double bonds, as in carbon disulfide, triple bonds, as in hydrogen cyanide, or, as you will see shortly, lone pairs. Three negative groups attached to a central atom attain minimal repulsions in the trigonal planar arrangement, which has an ideal bond angle of 120 degrees. We observe this angle in molecules with three identical groups, such as boron trifluoride and sulfur trioxide. Molecular shape is determined by the positions of atoms, not electron pairs. Therefore, if one of the electron groups is a lone pair, the molecular shape is not trigonal planar, but bent or V-shaped. Since a lone pair is held by only one nucleus, it is less confined in space and exerts greater repulsions on nearby bonding pairs. As a result, the bond angle is less than 120 degrees, as you can see in this model of ozone. Four electron groups around a central atom attain minimal repulsions in a tetrahedral arrangement, which has an ideal bond angle of 109.5 degrees. The tetrahedral shape is very common, especially in organic molecules. An example is methane, the simplest hydrocarbon. With one of the four electron groups, a lone pair, the shape is trigonal pyramidal. Since a lone pair exerts greater repulsions than a bonding pair, the bond angle is less than 109.5 degrees. Ammonia is a common molecule with this shape. Its bond angle is 107.3 degrees. When two of the four groups are lone pairs, the molecule has a bent or V shape. Two lone pairs exert greater repulsions than one, so the bond angle is reduced even further. Water, for example, has a bond angle of only 104.5 degrees. 4 electron pairs fill the valence level of a period 2 atom, but 1 from period 3 or higher can use d orbitals to expand its valence level and bond to more than 4 atoms. 5 electron groups minimize repulsions when they point to the corners of a trigonal bipyramid. Here we find 2 ideal bond angles. Equatorial groups lie 120 degrees apart, and axial groups lie 90 degrees away from equatorial groups. When phosphorus reacts with excess fluorine, the trigonal bipyramidal molecules phosphorus pentafluoride forms. Once again, when lone pairs are present, different shapes result. But a lone pair in an axial position creates 3 strong 90-degree axial equatorial repulsions, whereas a lone pair in an equatorial position creates only 2 90-degree repulsions. Therefore, to minimize the number of 90-degree repulsions, lone pairs always occupy equatorial positions. As before, lone pair repulsions reduce all other bond angles. With one lone pair, the object has a seesaw shape. Sulfur tetrafluoride is an example. With 2 lone pairs, the object is T-shaped, and the 2 remaining angles are less than the ideal 90 degrees. Bromine trifluoride is a T-shaped molecule. The final shape in the trigonal bipyramidal arrangement occurs when a 3rd equatorial lone pair repels the axial groups to 180 degrees. The object has a linear shape, as in the case of the triiodide ion. The final common arrangement has 6 electron groups attached to the central atom. Repulsions are minimized when the groups point to the corners of an octahedron, and thus lie 90 degrees apart. Sulfur hexafluoride has an octahedral shape. Unlike the trigonal bipyramid, all positions are equivalent in an octahedron. So one lone pair can take any position to give the square pyramidal shape, with all bond angles less than 90 degrees. Iodine pentafluoride has this shape. To minimize repulsions, a second lone pair must lie 180 degrees from the first. The 4 remaining bonding groups are repelled to the ideal 90-degree angle and define the square planar shape. Xenon tetrafluoride, one of the first noble gas compounds to be made, is a square planar molecule. Chemists use valence shell
Okay. I know that was a lot. So let's start by breaking down, and I'm going to use this document that I printed off for you. Once you have your Lewis structure, you can assign the bonding groups as X and the non-bonding groups as N. And that will allow you to determine this notation that's on the far left-hand column. A bonding group is a single bond. One bonding group is a double bond. One bonding group is a triple bond. So it doesn't matter what type of bond it is, it's just called one, as far as the bonding groups is concerned. Now, as you move across, then you get to what I call X plus N, which is the 4th column over. The X plus N ultimately tells you how many groups are repelling each other. If there's only two groups repelling each other, then the only option is a 180-degree linear shape. Think about it. If my hands represent two groups and I were to bring them close, because they contain electrons which are negatively charged, negative to negative, they're going to repel each other. They want to get away as far away as possible. So they obtain that minimal repulsion at 180 degrees from each other. And yes, I'll pass around my molecules so that you can see them a little bit easier. Now, three groups in that fourth column obtain minimal repulsion when they are 120 degrees from each other. And they obtain minimal repulsion when they make a trigonal planar structure. It's called trigonal because it forms a triangle. And it's called planar because every single atom is in the exact same plane. Now, you will notice that is the electron geometry for any time there are three groups. The electron geometry is trigonal planar because they are going to push so that they're roughly 120 degrees away from each other in the ideal bond angle. But if I replace one of the bonds with a lone pair, it's no longer going to be called trigonal planar for its molecular geometry. Because when we look at molecular geometry, the lone pairs aren't described. So now it's called V-shaped or bent. So as I pass this around, I want you to do two things. Number one, I want you to look at the electron geometry for three groups. And then I want you to cover up one of those groups, which indicates a lone pair, and see that see what the geometry looks like that's left over. And you will see that it is that bent or V shape. Now, when we get to four groups, whether they're bonding or non-bonding, they obtain minimal repulsion in what is referred to as a tetrahedron shape. It is called a tetrahedron shape because if you were to put sides on this structure, there would be four sides. So that's why it is called tetrahedron. Now, just like with the trigonal planar, if you replace one of those with a lone pair, the electron geometry remains the same. Even if there's a lone pair here, the electron geometry remains the same. But the molecular geometry changes. Now, if you replace it, it's called trigonal pyramidal because it looks like a pyramid with a triangular base. If you replace two lone pairs, or two bonds with lone pairs, it is still tetrahedral for the electron geometry. But when you describe the molecular geometry, you only describe what's left over, which is a bit or V shape. On the next page, you will see four structures for trigonal bipyramidal molecular, electron geometry. Anytime, now, once you get to 5 things on the central atom, it takes on what's called a trigonal bipyramidal structure. The reason it's called trigonal bipyramidal is because the center looks like a triangle. And if you were to take the center and set it flat on the table and draw sides, it would look like a pyramid. It's called bipyramidal because there's 2 of those, one on each side. Now, unlike the rest of the structures, trigonal bipyramidal has 2 different angles, and you can see the 120-degree angle in the equatorial position. Equatorial, folks, think equator around the middle, and axial is on the axis, up and down. So equator is, think of the Earth. It helps. Now, because the equatorial is 120 degrees from each other, that is where the lone pairs are going to go. And once you replace one with a lone pair, it has a seesaw shape. I got to remember, I'm way up here. It has a seesaw shape. When you replace 2 lone pairs, what's left looks like a T. And so you can play with it to see these different molecular geometries. Finally, we have an octahedron, which is on page 3. An octahedron occurs for the electron geometry anytime there's 6 things, whether those are lone pairs or single bonds or double bonds. As long as there's 6 things on the central atom, it will have an electron geometry of an octahedron. Now, because an octahedron, all of the angles are at 90-degree angles, it doesn't matter where you put the first lone pair. But what's left when you put that first lone pair is going to be a square, because the equator looks like a square, pyramid for its molecular geometry. Now, the second lone pair does matter because it has to go directly opposite. And so you have a square planar structure, because if you pop off the 2, all that's left is a square. And everything's in the same plane. These are in my office, and if you need to come by and me work with you on spatial visualization, I will do so. Now, during the lab, we've been developing electron configurations. I mean, not electron configurations. Lewis dot structures. Let's look at one. CO2. It has one carbon and two oxygens. Carbon's in group 14, the last digit is a 4, so it has 4 valence electrons. Oxygen is in group 16, the last digit is 6, so it has 6 valence electrons. The carbon contributes 4, the oxygen's 12, for a total of 16 valence electrons that must be distributed. Carbon is always the center of attention, so we're going to put our carbon in the center, around which we're going to place the oxygens. Using the Lewis dot structure rules, you then draw a single bond between the outer atoms and the central atom, and you subtract 2 for each bond you drew. We drew 2 bonds. 2 times 2 is 4, so we'll subtract out 4 electrons due to our bonds. That leaves us 12 electrons still to go. The next step says to give your outer atoms an octet. Our oxygen currently only has 2. In order for oxygen to get an octet, it needs an additional 6 electrons. And in giving our oxygens their octet, we have used up 12 valence electrons on those outer atoms. And so we have now hit 0. When you hit 0, everybody's supposed to ask, does everybody have an octet? Your oxygens, they have 8. Because we gave them their octet. But your carbon currently only has 4. So no, not everybody has an octet. So according to the rules, if not everybody has an octet, then you make multiple bonds. So we're going to bring in a pair of electrons. And when we bring in a pair of electrons to share, the structure that results is this structure. And you ask, does everybody have an octet? The oxygen on the left has 6 electrons in the lone pairs and 2 in the double bond, so yes, it has 8. The oxygen on the right has 4 in the lone pairs and 4 in the double bond, so it also has 8. But the carbon currently only has 4 in the double bond and 2 in the single bond, making it 6. Remember yesterday I said that chemistry liked symmetry. We need to make another multiple bond. We're going to bring in another pair of electrons, but we're going to bring it in from the opposite oxygen. And this structure results. Then you ask, does everybody have an octet? Your oxygens have an octet. They have 4 in the lone pairs and 4 in the double bond. Your carbon also has an octet because it has 4 in each of the double bonds for a total of 8. So this is the Lewis dot structure for carbon dioxide. Now, on our central atom, which I have listed as A, we have 2 bonding groups. We have 2 oxygens bonded to that central atom. And there are no lone pairs on the central atom. So this structure is an B2 structure. Where B plus N equals 2 plus 0, meaning it is 2. Two things obtain minimal repulsion in that linear structure. So our electron geometry is going to be linear. Now, because the two outer atoms are identical, and there is no lone pair, it means that the molecular geometry is also linear. And because it is linear, we know that the ideal bond angle is going to be 180 degrees. Basically, folks, I took this sheet and I went across in the process. Now, before I finish this problem, we need to watch the next video. And then I will finish this problem and do another problem.
Let's use valence bond theory, and especially the concept of orbital hybridization, to answer a fundamental question. How do the shapes of the molecules we observe arise from the orbitals of the isolated ground state atoms that bond? The hybridization concept proposes that in the molecule, the orbitals of the central atom have mixed mathematically and become hybrid atomic orbitals, new wave functions with different electron densities and spatial orientations. Let's begin with the simplest case and see how the theory accounts for a molecule with a linear shape. A key point to note is that the number of atomic orbitals that mix always equals the number of hybrid orbitals that form. Here, two different atomic orbitals, one 2s and one 2p, mix mathematically to become two identical sp hybrid orbitals, each with one larger and one smaller lobe. The two orbitals face in opposite directions in the atom. For clarity, we'll show hybrid orbitals in this simplified form. First, we'll use box diagrams to depict hybridization and consider the central beryllium atom in the linear molecule BeCl2. The isolated Be atom is filled 2s orbital and 3 empty 2p orbitals. In the process of hybridization, the 2s and one of the 2p's mix and form two sp hybrid orbitals. The two electrons from the 2s become distributed into the sp orbitals, one electron each with parallel spin. The two other 2p orbitals remain empty and unhybridized. Here is the same process in a box diagram that shows orbital shapes. Putting these ideas together, we can imagine the hybridization process for BeCl2 is something like this. The isolated beryllium atom with its filled 2s and empty 2p's, is shown with the small box diagram above. The chlorines have three 3p orbitals, but will fade out the ones that are not involved in bonding. In the molecule, beryllium has undergone sp hybridization. The half-filled sp hybrid orbitals overlap the half-filled chlorine orbitals to form two BeCl covalent bonds that are 180 degrees apart. From here on, we'll show electrons within orbitals as dots. To account for molecules with a trigonal planar shape, such as boron trifluoride, the model proposes that the ground state boron atom undergoes sp2 hybridization. The filled 2s of the central boron mixes with one half-filled and one empty 2p to become three half-filled sp2 hybrid orbitals. Boron's third 2p remains empty and unhybridized. Here's an orbital depiction of the ground state boron with filled 2s, half-filled 2p, and two empty 2p's. The fluorines have half-filled 2p orbitals. In BF3, the boron atom is hybridized, with the three sp2 hybrids pointing to the corners of an equilateral triangle. Boron and fluorine orbitals overlap to form three BF bonds 120 degrees apart. To account for the millions of molecules with tetrahedral shapes, the model proposes that the central atom undergoes sp3 hybridization. For example, in the carbon of methane, the filled 2s, two half-filled 2p's, and empty 2p mix and become four half-filled sp3 hybrid orbitals. The model describes bonding in methane this way. In the molecule, the carbon's four sp3 hybrid orbitals point to the corners of a tetrahedron. The H orbitals overlap them to form four CH bonds that are 109.5 degrees apart. For other shapes within a given electron group arrangement, the model proposes lone pairs in one or more of the hybrid orbitals. For example, the trigonal pyramidal shape of ammonia arises when the 2s and the three 2p's of the central nitrogen mix and become four sp3 hybrid orbitals, one which is filled with a lone pair. Here, we visualize the nitrogen atom undergoing sp3 hybridization. One of the tetrahedrally oriented sp3 hybrids is filled with a lone pair, and the H atoms overlap the other three to form three NH bonds. In the case of water, with its V shape, the model proposes a situation similar to that for ammonia. The 2s orbital of the central O atom mixes with its three 2p's and becomes four sp3 hybrids. But now, two of the hybrid orbitals are filled with lone pairs. In the water molecule, the oxygen has undergone sp3 hybridization. Two of the sp3 orbitals are filled with lone pairs, and the H atoms overlap the other two to form two OH bonds. Carbon is most commonly at the center of a tetrahedral grouping of single bonded atoms, but it also occurs at the center of a trigonal planar grouping that includes a double bond. Consider the carbon-carbon double bond in ethylene. Valence bond theory proposes that each carbon undergoes sp2 hybridization. Its filled 2s and two half-filled 2p's mix to become three half-filled sp2 hybrids, and the fourth electron occupies the unhybridized 2p. Let's examine the orbital view and highlight the two ways carbon orbitals overlap to create a double bond. Here, each carbon is undergoing sp2 hybridization. Note how the unhybridized 2p orbitals lie perpendicular to the trigonal plane of sp2 hybrids. The two sp2 orbitals facing each other overlap end to end. The bond they form is called a sigma bond. It is symmetrical along an imaginary line between the nuclei and is not weakened by the rotation of one atom with respect to the other. Now, focus on the two parallel 2p orbitals. By substituting accurate representations of 2p orbitals, you see that they can easily overlap side to side. This results in a pi bond, one that is not symmetrical along the line between the nuclei. Most importantly, it is weakened and in fact breaks by rotation of one atom with respect to the other. Thus, a double bond consists of one sigma and one pi bond. In the ethylene molecule, 4 H atoms overlap the 4 other carbon sp2 orbitals. Recall that in molecules with more than 4 atoms around the central atom, such as phosphorus pentachloride, the central atom utilizes d orbitals to expand its valence level. Hybridization accounts for the shapes of these molecules as well. In the ground state, phosphorus has a filled 3s orbital, 3 half-filled 3p's, and 5 empty 3d's. In PCl5, the 3s, all the 3p's, and one of the 5 3d orbitals mix to form 5 half-filled sp3d hybrid orbitals. The other 4 3d orbitals remain empty and unhybridized. Here is the ground state phosphorus atom with the 4 3d orbitals that remain unhybridized, omitted for easier viewing. We'll move back to see the hybridized p atom in PCl5. The 5 sp3d hybrid orbitals point toward the corners of a trigonal bipyramid, and half-filled 3p orbitals from 5 chlorines overlap them. Sulfur also has an expanded valence level in many of its compounds. In the ground state, it has a filled 3s orbital, 1 filled and 2 half-filled 3p's, and 5 empty 3d's. In the octahedral molecule sulfur hexafluoride, the 3s, all of the 3p, and 2 of the 5 3d orbitals of the central s mix to form 6 half-filled sp3d2 hybrid orbitals. The 3 unhybridized 3d orbitals remain empty. Here you see the isolated sulfur with 3s, 3p, and the 2 3d orbitals that will become hybridized. In SF6, the 6 sp3d2 hybrid orbitals point to the corners of an octahedron, and half-filled 2p orbitals of 6 fluorines have overlapped them.
Okay. I know that was a lot. It was worse than the VSCPR video for most people. That's one reason you have the opportunity to rewatch it. But let me break it down. Basically, folks, back when we were talking about electron configurations, if we looked at the valence shell for carbon and developed its electron configuration, it would have been 2s2, 2p2. Now, so what I've drawn is, or attempted to draw, is the S, the 2s, and the 3 2p orbitals. Now, if you think about those p orbitals, they point at 90 degrees. The fact of the matter is, if we simply look at atomic orbitals, we cannot explain the structures that we obtain. If you simply look at atomic orbitals, you can't get to a tetrahedron because there was only one thing on the axis. in that tetrahedron that I showed you. There was only one of these that sat on an XYZ axis. The rest of it didn't. So the fact of the matter is, we cannot use our understanding of electron configurations and atomic orbitals to explain the shapes that we see. We simply cannot use atomic orbitals to explain the shapes that we see, because 90 degrees to 109 degrees, that makes no sense. However, so basically what has happened is that these atomic orbitals have been hybridized to form molecular orbitals. And we can actually get to those hybridized orbitals that it kept describing by understanding the electron geometry. Okay, so I'm going to start a little statement over here, or a little thing over here, that's not directly related to our structure. Back when I asked you to draw box diagrams, how many lines did you draw for an S? How many lines did you draw for a P? And how about for a D? Okay. When we develop these hybridized orbitals, we develop them by starting with the S and then slowly combining them with P's to make the hybrids. Now the question is, how many P's do we combine? And when do we combine the D's? Well, that all comes back to this. I need a B plus N. My bonding groups plus my non-bonding groups equals 2, which made for an electron geometry that was linear. My bonding groups plus my non-bonding groups has to equal 2. So the hybridization for our linear geometry is SP hybridized because 1 plus 1 is equal to 2. We needed to combine 2 things to make the hybrid. We needed to combine an S and a P. So the fact is you don't have to be able to do all of that manipulation that was in the video. What you have to understand is that atomic orbitals cannot make the shapes that we observe. We cannot get these shapes from atomic orbitals. So we wind up with hybridized orbitals that are a combination of our atomic orbitals. The number of atomic orbitals that combine is directly related to how many we need in order to obtain that shape. Hopefully, once I do a couple more, it'll make more sense. Now, there is one more thing besides VSEPR theory and valence bond theory that we haven't talked about, and that is molecule polarity.
Sorry, can you go up just a little bit?
Once you draw your molecule with the correct shape, then you can determine whether the molecule is polar or non-polar. The simplest way, basically, folks, this gets into vectors, and I'm not going to get into vectors. But the simplest way to determine whether a molecule is polar or not is to assign the electronegativities of the atoms. That is the periodic table I gave you. And look for trends. If you look at oxygen, oxygen has an electronegativity of 3.5, whereas carbon has an electronegativity of 2.5. That comes directly from that periodic table. Once you've assigned your electronegativities, you look to see if there's a trend in the electronegativity direction. In other words, if I go from left to right, does it steadily increase? If I go in later ones, top to bottom, does it steadily increase? Does it steadily increase in one direction? No. This molecule, therefore, is non-polar. Now, if we'd have said yes, then we would have used a dipole moment arrow. Where the arrow would have pointed towards the more electronegative atom. And this little positive sign would have pointed towards the less electronegative atoms. I can make this somewhat more simple. at least to help you figure out whether it's polar or non-polar. But to determine the direction of polarity, you're going to have to use electronegativities. But I can help you figure out at least whether it's polar or non-polar, because your non-polar molecules will include hydrocarbons, of carbon and hydrogen only. It will also include linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and square planar. With one caveat to it. And that is if all outer atoms or if all outer groups are identical. Let's look at another example. And combine all this information. Let's do nitrogen trichloride. You have one nitrogen and 3 chlorines. Nitrogen is in group 15, the last digit is a 5, so it has 5 valence electrons. Chlorine is in group 17, the last digit is 7, so it has 7 valence electrons. The nitrogen contributes 5, the chlorines contribute 21, so you have 26 electrons to distribute around your molecule. The nitrogen is going to be the central atom around which we're going to put the chlorines. This is following those Lewis structure rules. You then draw a single bond between each of the outer atoms and the central atom, and you subtract 2 for each bond you drew. We drew 3 bonds, 3 times 2 is 6, so we'll subtract out 6 due to our bonds. That leaves us 20 electrons still to go. The next step says to give your outer atoms an octet. Our chlorines currently only have 2. In order to give them an octet, they need an additional 6. There are 3 chlorines. each needing an additional 6 electrons. 3 times 6 is 18. So we will have distributed 18 electrons due to our outer atoms. That leaves us 2 left to go. The next step says if there's any remaining after you've given your outer atoms an octet, they go on your central atom in pairs. So we're going to place our lone electrons on the central atom in pairs. And we hit 0. When you hit 0, you can only manipulate what's there. But when you hit 0, you ask, does everybody have an octet? Your chlorines have an octet because they have 6 in lone pairs and 2 in double bonds. Your nitrogen also has an octet because it has 6 in the single bonds and 2 in the lone pair. So yes, everybody has an octet. Now, we need to figure out the electron geometry, molecular geometry, hybridization, and all of that jazz. So we have our central atom, and folks, everything's about the central atom at this point. Everything is about the central atom at this point. Attached to that central atom, we have 3 groups that are bonded to it, which I think actually are an X on yours. I use slightly different. And we have 1 lone pair. So when we look at this, our structure is an A, B, I'll keep doing that. A, X, 3, N. X plus N is 3 plus 1. So in other words, we're looking at 4 groups. Anytime there are 4 groups, then the electron geometry is tetrahedral. Therefore, if I were to draw this in a tetrahedral format, I would draw it using this structure. By the way, when I illustrate a 3D object on a 2D screen, bonds that are lines are in the plane. So in other words, this chlorine and this nitrogen are in the same plane as the nitrogen. I'm sorry, the chlorine and the lone pair are in the same plane as the nitrogen. When you have a darkened wedge, it means that it is coming to you. And a dashed wedge means it's going away, so it would go behind the board. This is how we illustrate something that is 3D in a 2D form. Which you will notice I use that diagram in the diagram that you have printed. Now, because X plus N is equal to 4, then we know S is 1. P, we need 3 because 1 plus 3 is equal to 4. So the hybridization is going to be sp3 hybridized. Now to describe the shape. When you describe the shape, remember, you don't pay attention to for the molecular geometry. You don't pay attention to the lone pair. So what does the rest of this thing look like? Looks like a triangle with a pyramid. So it's molecular geometry. It's trigonal pyramid. Now for the polarity. Chlorine is 2.8. And nitrogen is 3.0. Is there a direction where these numbers are increasing? Do they increase going up? Do they increase going right? Do they increase going left or down? They increase going up. So this is a polar molecule. And therefore you would draw a dipole moment arrow. Yes. Oh, I've goofed. The chlorine is a 3. Which actually is a good thing for me to have also, because anytime you have a lone pair, it's going to point towards the lone pair unless it's obvious. Sorry about that. I looked at bromine. You will get the periodic table of electronegativities on the test. I don't actually test over electronegativity because you get the periodic table of electronegativities on the test. Questions? Okay, just some FYI. Number 1, I will be in my office until 3 o'clock today. Well, 2:45. Feel free to stop in and ask questions. Number 2, on Tuesday, I will do a couple more of these problems and add one more piece to these problems. And then we will also move on to other material that day. Number 3. I found out Tuesday that they don't have my chemicals for next week's lab. So we do not have lab next week. So I will be in my office all from 8 to 2 next week and can answer questions. So I'm making, so you can come during your lab time and ask me questions, or you can come at another time and ask me questions. So anyhow, that's where we stand. Yes. We are not gonna have a lecture during lab next week. Oh, thank you, yes. Today during next period, there is the opportunity to earn bonus points. Basically, it is, you need to double check on Blackboard to make sure that you know where, but I think it's the Snow Fine Arts practice recital hall. But it may be Reynolds. I think it's Snow Fine Arts. And it's during X period. To get the bonus points, you go, you take notes, you bring them back to me next Tuesday for your bonus. Any other questions? And the food bonus is due next Thursday. Yes. You can bring the food bonus on Wednesday to my office if you want. I'll be in there all day. I will see you on Tuesday. I'm excited. I forgot to send it around. I just realized that. Yes. So the equipment that you sent out is that has all, I think all of them on there. But no, it does not. It has all of the iron that the sheet that I passed out has everything. Okay.
How do you recommend studying? Like just memorizing stuff? Or?
Part of it's memorization, part of it is just doing a lot of problems.
I just because there's so much information. I was like, okay.
The best thing is to actually do a lot of problems.
Just over and over, just do more problems.
Yeah, that's why there are so many of them. And then so many examples and so many is because it's part of it is memory work, but then the other part is just
doing it. Yeah.
Tetrahedral's missing. I had stolen tetrahedron.